Okay, picture this for a second. You're holding a massive, heavy rock in your arms. You're holding it completely still, but after a few minutes, your muscles are shaking, you're sweating, and you feel absolutely exhausted. I mean, you've clearly done a lot of work, right? Well, in the world of physics, if that rock didn't actually move, the amount of mechanical work you just did is exactly zero. I know, it sounds crazy, but welcome to this Grade 8 Physical Science Explainer, where we're going to unpack exactly why that is.
So, here is our roadmap for this explainer. First, the illusion of work. Second, defining work and power. Third, the work-energy theorem. Fourth, let's pause and check. And finally, number 5, a quick recap and transfer challenge. Let's just jump right in.
Section 1. The illusion of work. Okay, let's dive into this.
You know, the everyday way we use the word work is kind of setting us up to fail in physics class. In our daily lives, work is just anything that requires effort, right? Doing your math homework, that's work. Holding that heavy rock stationary until your arms are literally burning definitely feels like work. But physics is incredibly strict about this. To a physicist, work requires two very specific things: a force being applied and an object moving a distance in the exact direction of that force. So hey, I completely validate your physical exhaustion from holding that stationary rock. You are definitely using biological energy to keep those muscles contracting. But because that rock isn't traveling over a distance in the direction you're pushing, the mechanical work done on the rock is absolutely zero. Homework? Yeah, also zero mechanical work, unless you count the tiny distance your pencil is moving across the page.
Section 2. Defining work and power. Now that we know what work isn't, we really need to lay down the precise rules for what it actually is. Here's your golden rule for this explainer. Work is the application of a force to move an object over a distance in the direction that the force is applied. When you get down to the math, it's literally just force multiplied by distance. When you apply a force, which we measure in newtons, over a distance measured in meters, you get Newton meters. But we actually call that unit a joule, proudly named after the brilliant physicist James Joule. Every single time you successfully lift a rock off the ground, you're applying an upward force to overcome gravity, and you're moving it an upward distance. Bam! That is work measured in joules.
But what if you lift that rock really, really fast, compared to, say, taking all day to do it? Well, that is where power comes in. Power is simply the rate at which work is done. It takes the exact same amount of work to lift a heavy object up one floor, totally regardless of your speed. But if you do it faster, you're generating more power. We calculate this by taking the work done and dividing it by the time it took. We measure power in watts, named after James Watt, the engineer who famously improved the steam engine and pretty much kicked the Industrial Revolution into high gear.
And this brilliantly illustrates the real difference between work and power. Just imagine two people moving identical flat-screen TVs up to a fourth-floor apartment. The woman uses a clever mechanical pulley system on the balcony, and she hoists the TV up in just 2 minutes. The man, on the other hand, decides to carry his TV up 4 entire flights of stairs, which takes him a grueling, sweat-inducing 5 minutes. Assuming they moved those TVs the exact same vertical distance, they did the exact same amount of work on the TVs, but the woman generated significantly more power. Why? Simply because her time, the denominator in our power equation, was much smaller.
Section 3. The work-energy theorem. Let's see how this builds into one of the most elegant concepts in physical science. Because when you do work to move an object, you aren't just shifting it around. You're actually transferring energy. Energy, at its most fundamental level, is really just the ability to do work. They're so closely related that they actually share the exact same unit, the joule. Now, moving objects have what we call kinetic energy, which is the energy of motion. The work-energy theorem states that when you do net work on an object, that work is directly transferred into a change in the object's kinetic energy. If you push an object to speed it up, the work you put in perfectly equals the kinetic energy the object just gained.
Let's look at a quick example to see this theorem in action. Picture a 50-kilogram ice skater, smoothly gliding across the ice at a constant 8 meters per second. Suddenly, a friend skates up from behind and gives her a solid push in the forward direction. Thanks to this applied force over a distance, the skater's speed shoots up to 12 meters per second.
So how much work did that friend actually do? Well, using the work-energy theorem, we don't even need to know the exact force or distance of the push. No way! We just find the difference in our kinetic energy before and after. Since kinetic energy is 1/2 times mass times velocity squared, if we take her final kinetic energy and subtract her initial kinetic energy, the math works out perfectly to 2,000 joules. The friend did 2,000 joules of mechanical work, which transferred seamlessly into 2,000 joules of extra motion or kinetic energy for the skater. It's like a giant perfect puzzle.
Section 4. Let's pause and check.
Now, what's really interesting about these concepts is how tricky they can be if you aren't paying close attention to the definitions.
So I want to challenge you to use what you've learned. Here's your first pause check. Imagine you successfully lifted that heavy rock we talked about earlier, and now you're carrying it in a perfectly straight path across your front lawn at a constant speed. Are you doing mechanical work on the rock while you're walking? Go ahead and pause the explainer. Really think about our exact definition of work, and when you have your answer, hit play.
Okay, the answer is a resounding no. I know it feels like work, but remember Newton's laws of motion. No net force is required to keep an object moving at a constant velocity. You are certainly applying an upward force to fight gravity so you don't drop the thing, but the rock isn't moving upwards anymore. The direction of your force and the direction of the rock's movement must align. Since you aren't applying a net forward force to maintain that constant forward speed, the mechanical work done on the rock as you carry it is zero.
Awesome. Let's try one more. Pause check number 2. Which of these two scenarios generates more power? Carrying a heavy 100 Newton TV up one floor in 50 seconds, or carrying a much lighter 24 Newton watermelon up that exact same floor in just 10 seconds? Pause the explainer, remember your power equation, and let's see if you get it right.
All right, let's look at the math. Power is work divided by time, right? And work is force times distance. Since the distance up the floor is exactly the same for both, let's just look at the ratio of force over time. For the TV, 100 newtons divided by 50 seconds gives us a power ratio of 2. But for the watermelon, 24 newtons divided by 10 seconds gives us a ratio of 2.4. So even though the watermelon is so much lighter and required way less work to lift, the fact that you did it in a fraction of the time means you generated more power carrying the fruit.
Section 5. Recap and Transfer Challenge. So, the absolute crucial point here is that time and direction change everything when we analyze physical exertion.
To sum up our grade 8 physical science journey today, mechanical work only happens when a force causes an object to move a distance in that exact same direction, and it's measured in joules. If the object stays stationary or moves without a net force in the direction of travel, zero work is done. Power is just how rapidly you accomplish that work, measured in watts. And the beautiful work-energy theorem proves that work isn't just some abstract idea. It is the literal transfer of energy, directly changing an object's kinetic energy of motion.
Before we go, I want to leave you with a final transfer challenge to really spark your curiosity about energy systems. Imagine a massive 10,000-kilogram truck driving down a steep 75-meter hill. To stay safe, the driver rides the brakes to maintain a steady, constant speed all the way down. Because the speed is constant, the truck's kinetic energy doesn't increase at all, but it just lost a massive amount of height, meaning it lost millions of joules of gravitational potential energy. Now, the law of conservation of energy says energy can't just disappear, so if it didn't turn into kinetic energy, where did it go? I'll give you a hint. Think about the mechanical work those brakes are doing, and the massive amount of thermal heat being generated in the process. It's a fascinating display of energy transfer in the real world. Thanks for learning with me today, and keep questioning how the physical world works.